Okay, today we'll review for the exam. I've made it really clear in the last 2 Tuesdays what the topics are that can be on the exam. So you tell me, what could we have for the calculus-based question on the exam this afternoon?
Inertia.
Calculate the moment of inertia?
And center of mass.
Or the center of mass. So it's going to be one of those two. Now I have here another thing that would fit into this material. That is calculating the force or torque due to water pressure on a dam. That is not going to be on the exam. So, two topics with solids, and these are the only two topics we have. We either have calculating, and I just put the x center mass because you can do x center mass, you can do y center mass by changing x's to y's. X center of mass is equal to the integral of x dm over integral of dm. And the I about some axis is equal to the integral of r perpendicular squared dm. So those are the equations you're going to use, either this one or this one. And then we have to be able to say, well, depending on our distribution, it could be a linear distribution. Dm is equal to lambda, I put dx here, or it could be an areal distribution, so dm is sigma dA, or it could be a volumetric distribution, dm is equal to rho dv. And what I won't do is I won't choose something that makes you have to do really hard integration. Right? I don't want you to spend all your time like, ooh, can't remember how to do this integral. So you should be able to do, polynomial integrals or like e to the x type integrals. But I'm not going to have something that's like x e to the x, because you either have to have an integral table or do integration by parts. And while you're supposed to know how to do integration by parts, I don't want that time to be spent on the exam. Now, here's the stuff that won't be on the exam for fluids. Finding the pressure as a function of depth, dp equals rho g dx. We'll talk about this next week in class. Finding the force as a function of depth, df is equal to p, the pressure, dA, and find the torque, d torque is equal to cross. We'll talk about those next week. So let's just do examples. Let's have fun solving problems. And I say have fun because to me it is fun. To you guys, it may or may not be. I recognize that not everyone enjoys solving a problem. So let's start with the first one. Let's suppose that we have a rod of length L and we want to find its center of mass, and it does not have a constant density. So we start with our equation. X center mass is equal to the integral of x dm over integral of dm. Okay, and what do you see here? You see what?
Okay, it's almost the same thing on top and bottom, but it's an X.
But there's an X on top, right? That's the difference in the top and bottom. The top is an integral. I just said we're not going to have to do this because you either have to have an integral table or do integration by parts. But I've gotten as far as I can do without having to do the integration by parts. I'm going to stop here simply because, the bottom integral, you should be able to do that one in your head. integral of e to the minus x over L dx. You divide by the exponent, well, the derivative of the exponent. The derivative of the exponent is minus 1 over L. So you divide by minus 1 over L. So the bottom is going to be minus lambda 0 L e to the minus x over L, going from 0 to L. That one we could do. The top one is a little more, integration by parts is not hard, but we won't spend the time. So that's how we would do the one-dimensional one. The two-dimensional one, starts the same. dA is dx dy. Now, because I have two d's, I'll put a second integral sign there. Was that?
Is that sigma on the bottom?
Yeah, that's sigma. And now my sigma is sigma aught xy. All right, how's this fit with your plans? Is this something that is easy or hard to integrate? I'm going to take it by your response that you're believing it's hard. Well, let's separate what we can. Sigma aught was a constant. Then I'll put my x stuff. Then I'll put my y stuff.
So we separate dx and dy.
Right, because there's nothing tying to x and y, there's not a parenthesis x plus y. I can move the y integral through the x because the x is dependent on y. And now I have two simple integrals. Now I do have to pay attention to my limits, and I had length of L and width of W. So let's say the length is x and the width is y. So the x integral will go from 0 to L, and the y integral from 0 to W. So there's my top, and my bottom is this is not red. Now, if you look at this, we can cancel. That's 1. That's 1. And so what I'm left with is just the red integrals. Now, I skipped a step there. It's L cubed over 3 minus 0 over L squared over 2 minus 0. There. Now I didn't skip any steps. And because of the symmetry of this, in the y direction, it would be 2/3 W.
What's the answer again?
The answer was 2/3 L. And if you're doing the y, in the y direction because your integral is going from 0 to w instead of 0 to L. And because of the symmetry, the greens, if I was doing the y, the greens would be y squared on top and y on bottom. So it'd be 2/3 w. And then the final option here.
Wait, why would it be y squared on top and y on the bottom? Why wouldn't it be y squared on top and y squared on the bottom?
Well, for the x integral, for the one we did, it is.
Yeah.
But if I was doing the y center of mass,
Yeah.
if I'm doing the y center of mass, then I'm going to have this equation will replace x with y, so it'd be integral of y dm. That's right. Now we have the center of mass for sphere of radius r. For the sphere of radius r, what's the first thing that you're going to do that's different from what we just finished doing? Choose a different coordinate system, one that matches the symmetry of a sphere. And so I would do the x equals r I got to remember which angle's which.
I think it's O theta then phi, right?
I actually have to think about it. It's so embarrassing. I'm pretty sure is theta. And so cosine theta. The going all the way around circle is the phi part, and the theta is measured from vertical down. So actually from vertical down? Yeah, if it's measured from vertical down, then I have those backward. The z would be r, or no, z is r sine theta. No, I did it right. No.
Alright, so P
I think we know what
P
question
is the horizontal. So P is the horizontal measure.
The phi is the one that's going from 0 to 2 pi.
Okay. Around the equator.
Yeah, around the equator. And then theta is going from pole to pole.
Okay.
If we were to see this on an exam at some point in time, would we?
Yeah, we would have those.
Those would be given.
Yeah.
Okay.
Because you don't want to be like me going through like what, huh? So we would have this, and then we have dv is equal to that. And so we would have the x center mass there's my x times all over the integral of and so now you have a more complicated integral, but it's not the worst thing you've seen.
Is that cube? Right on cube?
Yeah.
Yeah, that's a cube. I started writing a square and realized halfway through that that's a cube, and so I ended up with funny. So we have this integral on the top. On the bottom, I will have
Is that pi over 0? The part. Oh, yeah, that's fine.
now the denominator is a good way to check to make sure we have things correct. The numerator is going to be the thing that gives us our answer, really. What's the integral of r cubed dr? R to the 4th over 4, going from 0 to r, that's r to the 4th over 4. What's the integral of cosine phi d phi? I believe it's positive sign.
I was forgetting.
Doesn't really matter because what's sine of 2 pi?
Oh, it's just 1. No, it's 0.
Sine of 2 pi is 0. What's sine of 0?
What else?
0. Hence, this is 0 minus 0 is 0. And then we have the integral of sine squared theta d theta. We could do it, but I don't care at this point. Don't care. Because I have 0 times whatever it is. I don't need to go any further. The denominator, like I said, can be just a check to make sure we're doing things right. Integral of r squared dr is r cubed over 3. Integral of d phi from 0 to 2 pi is phi. Going from 0 to 2 pi is 2 pi. And integral of sine theta is minus cosine theta. Cosine theta of pi is minus 1, so minus a negative 1. And then somehow my brain's going sideways on me. I know this last term is 2. Minus negative 1 is 2. And so that gives us on the bottom 4/3 pi r cubed, the volume of a sphere. And I forgot to put my sigmas here, or not my sigmas, my rhos. The rhos will cancel out, of course.
So what is this one? Instead of the 0, just cancel it out the top.
What was that?
So wait, what does this all come out to?
0 times anything is 0, as long as you're not dividing by 0.
So what were you saying about the whole 2 pile and something? Are you talking about the bottom half?
The bottom house, this here, should be the volume, right?
Okay.
It's the volume times rho. And so it gave us indeed rho times 4/3 pi radius cubed. So it was, that was just a check to make sure we did our calculus right and our equations were set up right, as far as we can tell. Okay, so that would be the x center of mass. Now if I go to the y center of mass, okay, where's my x, y, and z? I wrote them here somewhere. Oh, up here. So if I do the y center of mass, I'm going to have sine instead of cosine for this integral here. In the end, I'm still going to be integrating cosine, which gives me sine, and going over a single period. The area for a single period of a sinusoid is always going to be 0. Yes?
Wait, so which integral? So you pointed at your screen, but I don't know.
Okay, the difference in my x variable and my y variable is that, changing the cosine phi to a sine phi.
Which integral are we changing?
And so if I'm changing this to a y center mass instead of an x center mass, I'm going to replace the cosine with the sine, the cosine phi with the sine phi.
Okay.
So this would be a sine phi, which means that when I get to my integral, I have the integral of, can you see where my finger? Well, kind of. Yeah, kind of there. That cosine phi will be a sine phi, which you will integrate to a minus cosine phi. And just like before, a sinusoid over a full period integrates to 0. And so that gives us 0. So we have 0 for x and y. I don't really need to do any more than one of them, because if it's spherically symmetric, we know we're going to get 0 for all three, right? It can't be 0 for one and not 0 for the others because of symmetry. But if I do the z direction, just for completeness, I'm going to have r cosine theta, so there will be no sine or cosine phi in there. And I will have a, right, so this, the term that still has that little curve, well, that now disappeared. Okay, that term there is going to just be integral of d phi. There will be no cosine or sine. And this one here, the last one, instead of sine squared theta, it's going to be sine theta cosine theta. And then we have to, well, to do this quickly, sine theta times cosine theta can be written as a sinusoid just starting at a different angle. And so it's still going to integrate a sinusoid over a single period. So that would still give us 0 again. Most complicated of my 3 options here that I had written out. Now, will you get exactly one of these? No, it could have a different equation for what lambda or sigma or rho is. But the process would be the same. So any questions about the center of mass process?
So even though we'll have some changes, that doesn't change the fundamental that the sphere is always, like the x, y, and z on a sphere won't be different from each other.
If it's a spherically symmetric,
Yeah.
then yes. I mean, if it's spherically symmetric, you know the center of mass has to be the geometric center.
Yeah.
But you can't just say, it's spherically symmetric, it's the center.
Yeah.
If I ask the question for the simple point that I'm going to say, use calculus to show.
It just for the way of checking. We don't deal with any non-spherically symmetric, do we?
You would use spherical coordinates at this point if it wasn't spherically symmetric. We will talk about some weird situations in quantum mechanics if you choose to take the class, where we'll use spherical coordinates and we won't have things work out as simply. Okay, then moment of inertia calculations. Moment of inertia calculations in many ways is the easier calculation because it only has the one integral instead of the 2 integrals. What makes it harder in some sense is that you have to have that r perpendicular. So remember in class last week, we went through, we identified what coordinate system am I going to use, what is the equation for my r perpendicular in that coordinate system, what are my limits for integration, and then doing the work. So if you were to have this on the test, you would need to write down your, I'm going to choose this coordinate system because of this reason. And my r perpendicular is this, and my limits are this. Actually write that down, and then do the integral. So once again, I gave a one-dimensional rod of length L, and I did not specify where we're rotating it around. I would need to specify where we're rotating around. And the obvious thing to do here is to rotate around the end of the rod. So if I'm rotating about the end of the rod, r perpendicular is going to be the perpendicular distance from the end of the rod to where I have the little piece of mass dm. And so my r perpendicular is just going to be equal to x. So life is easy. And so I have integral of x squared, r perpendicular squared, times dm, which is going to be
What is that in the parentheses?
lambda 0 e to the minus x over L dx, which is the lambda value. The starting equation, something is, I don't know why OneNote's no longer remembering my pages from this equation right here. So it's r perpendicular squared dm. And so I put in the value for r perpendicular and of course squared it. So that's why it's x squared. And then the dm is sigma dx. So now this is x squared e to the minus x over L. Once again, I'm just not going to give you that integral because I don't expect you to be able to just do that one off the top of your head. I could give you something that was like, the lambda is equal to x, times lambda 0, something like that. Just not going to give you something that's more complicated. Okay, rectangular sheet with the same sigma as before. So if I have a rectangular sheet, we have to decide where are we going to rotate this about. It's going to be given to you in a problem. So how would you want to solve this for an example? Where would you want to rotate it about? And I'll take anything except for rotating about one end so it's going like this. The reason for that is because that makes it simpler than I want to do.
So you want the rod to rotate like around the center?
Where do we want to rotate it about?
Which one do that?
Okay, he said a corner, and he said the center. I am, now I think about this, I'm going to choose to rotate about the corner like that. It actually comes out to be the easiest. So that I have x is this, y is this. Here's my little piece dm equals sigma dx dy. And the r perpendicular is x squared plus y squared, square root. And so I would have I is equal to integral r perpendicular squared, so that's going to be x squared plus y squared, times my sigma 0 xy dx dy.
Shouldn't that be in square root?
It's the square of the square root,
Oh,
right? Because it's r perpendicular squared.
So that's sigma. What's in between that? Is times. What's in between?
That's times x times y.
Okay.
This right there.
Okay.
X between x squared and y.
X squared y plus y squared x. And so now this is a fairly simple integral. Because if I do my x integral first,
Wait, there are two intervals in there.
yes, there's two integrals. So I'm going to do my x integral first. So the integral of x squared y dx is x cubed y over 3. Integral of y squared x dx is y squared x squared over 2. So there I just did my x integral. Now I didn't put in the limits yet. Since the lower limit is 0, putting the limits is kind of simple. It's just going to be L cubed y over 3 plus y squared L squared over 2. Then you do that integral. It looks very similar, right? And so finally we put in our limits. Factor out what you can. And there I have the moment of inertia for spinning it about the corner. I don't know about you guys, but I always feel really satisfied with myself when I do a problem like this. Not so satisfied with myself when I try to find where I am on the paper and find that I'm below my last, that was my last slide. No wonder I was below it. The last option, the moment of inertia for sphere of radius r. Well, what axis should we rotate it about? Clearly, we're going to rotate it about one that goes through the center. Should we align that with the x-axis, the y-axis, or the z-axis? Or somewhere in between if we're road buttons for punishment. Which one's probably going to be easiest? Probably doing about the z-axis. So we'll do it about the z-axis, which means that our perpendicular is going to be the square root of x squared plus y squared that we had before, right? So if we go to the x and y here, we're going to have, each one has r sine theta, and then one has cosine phi and one has sine phi. I didn't pay attention to which one was which. Well, because I have them both, it doesn't matter what order I put them in. And of course, cosine squared plus sine squared is 1. So it's just r cosine theta. And so then I about the z-axis So we have that integral to do, which gives us integral from 0 to capital R of r to the 4th dr, integral from 0 to 2 pi phi, integral from 0 to pi cosine squared theta sine theta d theta. First two, and I forgot to put the rho out here, rho. What's the integral of r to the 4th dr? R to the 5th over 5. putting in the limits already, we have that. Integral from 0 to 2 pi of d phi. 2 pi. Integral of cosine squared theta, sine theta d theta. That should come straight to the three of you. Right? You didn't do this on a test a couple weeks ago. They did. If you let u equals cosine theta, what's du equal to?
Oh, to use the sine theta, d theta.
Yeah, it's I think minus sine theta d theta, right? Yeah. And so this is just minus u squared du. Integrate that, and it's minus u cubed over 3. And of course, cosine of pi is again minus 1. Minus 1 cubed is still minus 1. Minus a minus 1 is a plus 1. So it's 1/3 minus a negative cosine of 0 is 1. So 1/3 minus 1/3 minus a negative 1/3 is 2/3. I'm factoring out rho 4/3 pi r cubed. The reason I'm doing that is because that's mass. And what I'm left with is an r squared there and a 2 over 5. Just let me do color coding so you see where the there's where I got the 2 over 5. And since it was a superscript of 5 here, that gave me 3 and 2.
Would we have to be able to simplify it like that, or if we left it?
I would probably count it right either way. I like to put it this way because I know I'm right, because I know that's the equation. So I get to the end and I'm like, yes, I did it right. All right.
What can I see the answer at the very bottom? Okay, 2 pi.
So for the exam, your calculus specific question is going to be similar in nature, not exactly anything we did here today, but similar in nature to one of the problems we did today. So if you have any questions about the problems we did today, now is the best time to ask them.
Okay, so this was just generalizing for a sphere, right? Moment of inertia for a sphere.
This, not generalizing, it was calculating. Moment of inertia for a sphere, yeah.
Okay. So the only exception is if, like, it had so these are just variables and constants that were individually calculated for it, right? Not like a specific number that we put in for it.
Yeah, I didn't give you the radius of the sphere because it just works for any radius.
Okay.
Now let me ask a question, something that's a little different. What if I had asked you to find a moment of inertia for a hollow sphere? What would be different?
The mass would be distributed around the edge.
Yeah, the mass is only on the edge. So what is that going to change about the work we just did?
Just checking the density on it. No.
Well, we'll say that the part that has mass has constant density in rho. What's fundamentally changed by doing a hollow sphere instead of a solid sphere? Okay, let's think about the steps of the process. First step, what was the first step we did for finding mode of inertia? Determining coordinate system. Second step. Okay, is the coordinate system different if it's a hollow sphere? Shouldn't be. Second step.
Figure both perpendicular.
Are perpendiculars. Are perpendiculars going to be different if it's a hollow sphere? Still going to be the same. What's the third step?
We chose a point, like X, Y, Z.
I didn't follow.
We did this from the Z coordinate folks.
Yeah, the z about the z
That's
axis.
what our next step was.
Oh, determine what axis we're doing about that. That would. It is an important step.
Now we
Because we could have chosen other axes to do it about and made our lives harder. But the third general step. We've determined our coordinate system, we've determined what are perpendiculars, what else do we have to determine before we integrate?
formula. Like, it won't will O squared change if it's not. So another way we can be given a bunch of different, like what it will equal whether or not it's a hollow or a solid sphere.
Well, what's going to change is our limits. Because it's actually only going to be a two-dimensional integral because r is a constant now. So I would only have the d theta d phi, and my r would be fixed. And so I would, instead of having the integral of r to the fourth dr, I would just have r to the fourth. And so my answer is going to not have the over 5 portion because you just don't have that. Now, there is one other thing then that comes into this. The mass isn't going to be 4/3 pi r cubed times density either. And so the equation is going to be different because of that aspect. And what you would generally actually do is you're just going to integrate over the surface, and so you'll have a sigma d area and so on. All right. Any questions you have for me? And you can ask questions about anything for the exam, not just calculus based.
Is this exam harder than the last one?
Is what?
Is this exam harder than the last one?
It shouldn't be.
Okay.
It should all be of roughly similar difficulty.
With laminar and turbulent flow, do you want us to know like how far do we have to know calculation wise?
You don't have to know calculation.
Okay, just like layers and
Yeah.
okay.
Or just know the difference between laminar and turbulent.
Yes.
Okay. And is there some sort of like Reynolds number? About
There are, but we didn't get to that.
Okay.
For the 2 and 3 dimensional aspects of this, will it say if we are not dealing with something that is equal? Like with the spherical, it's an equal sphere, but like for the, all the things should have to be the same for the center of mass. Like
Uniform.
Yeah, uniform.
I
know that
if it's spherical, you could have the a density that varies with r only. It's not going to vary with theta or phi because that would break up the spherical symmetry.
I mean, for like the 2-dimensional, I know that it will just give us different limits, which is what will change that. But if we have like 0 to W and 0 to L, obviously we really only need to solve for one of them, and then the other one should be the same because they're the same limits.
If it's rectangular.
Yeah.
And unless you have a density that only changes with x and not with y or something like that. All right, well, let's go. I'm going to finish writing your test. Yeah. I'll see you all in an hour and 45 minutes.
Time will fly.
Because you'll be having fun.
Oh, I have to have lunch first.
Yeah.